My name is Guiherme, and I will talk about recent developments to improve parallelism in the root I/O system. We know that this is a very important part of root, and we want to make it faster. So I'll start just with an introduction. What root I/O means. It's much more than just disk access. And then I'll talk about some efforts from the root team and also from external contributors to improve parallel reading and writing of data in root, and then just give a bottom line and outlook. So as I just said, it's much more than just reading from the disk. We need to read the data, inflate because it's compressed, deserialize, and then once everything is processed, to deserialize, deflate, and write out. And that's also not the only thing that is involved. So the user can choose the granularity, how to store the data into clusters of entries. There are also interactions with other parts of root. So if root is reading some type that is not known yet, maybe it would need to load some dynamic libraries that contain these classes. So it has to query the type system to know how these objects are represented in memory and so on. So the objects can be also chosen by the user to be stored either in column-wise, the whole event, let's say, together, or if you have a class with many members, you can choose to split the members and store each of them in different baskets or columns. So there are several ways of parallelizing this complex system. So we can process for data that has many branches, like reconstruction data, to a lesser extent the analysis data. So if you have 50, 100 branches, you can just read branches in parallel. And you can also read more data in parallel than just a single entry. You can read data in bigger chunks. And these strategies are not mutually exclusive. Actually, it's very good that if we can nest parallelism and do both things in parallel. So since root has many of these phases, read, deserialize, and decompress, so on. So each of them can be parallelized independently. And root has been using, so the runtime support for this nested parallelism is crucial, and root has been using internally thread building blocks from Intel. And you get it enabled by configuring root with enable implicit MT. And when you write some code that you want to be to do your work in parallel, you call root enable implicit MT, and then these things will be enabled. So let's start with reading. So the first is reading a single file in parallel. Since version 606, root supports reading the same file from multiple threads in parallel. So you just create a T-file class, you open the same file, and then you can read things in parallel. So root manages all the non-trivial interactions with the type system to load the things that need to be loaded, libraries or the classes, and so on. And so you can also parallelize, so you can parallelize the reading of branches and reading of multiple entries of the same branch. And this is basically transparent to the user. You don't have to write any special code for this. So here is an example from Brian Bachman. It's reading CMS and Atlas data. So this is just reading, decompressing, and deserializing two data sets. So with the CMS, you have 70 branches of simulation data. With Atlas, some more branches and XAOD data format. And we have to emphasize that this is not just parallel 4. There are a lot of interactions. But on a laptop with 4 cores, you see here the hyperthreading line, you can get 3.5. Of course, that if you have a bigger machine, this can scale up more. So you're basically limited by the I/O performance of your media. So, and this has been available since 608, parallel reading of multiple branches in parallel. So the other approach is decompressing baskets in parallel. So if you have 70 branches, but you also want to read many, many entries in parallel, you can do parallel decompression of baskets. This is work in progress. It's more recent effort. So it's not yet in root, but it's already on GitHub as a pull request under review and testing and so on. So the concept is to use the T3 cache. And as you fill the cache, you start processing it, but you also launch a new task to fetch more data and decompress it while you're processing the current cache. So, and then once you're done processing the cache, hopefully the data that you fetched before will be already processed and decompressed. Then you can process that data immediately. So with this, you have some effects. So if you have multiple threads trying to read data, sometimes you will read some same cluster more than once and decompress the same basket more than once. So the speed up is not as impressive as with the reading of multiple branches in parallel. But of course, that if you have 3 branches, then you cannot parallelize too much in the number of branches. You have to do something like this to read baskets in parallel. So this is just root event data with a fully split data set and tested on a laptop as well. So now that talked about reading, let's go to writing. Actually, I want to mention one thing that I couldn't put here, but is also very interesting is the bulk I/O that was presented before, and there is also a poster that you can see. So please visit the poster by Brian Bockamon on this. So for parallel writing, since version 606 also, root supports writing to different files in parallel. So if you have some generation of events and you want to save the data in a T3, you can create multiple threads that will generate the events, and they each write to a single file. And then at the end, you have as many files as you had threads in your program. So this is not transparent. You end up with many files that you have to merge at the end. So the full cost of creating this data is not there. So that's one reason why there was an effort to parallelize HAD, which is a tool for merging root files with similar structure. And this situation needed an improvement. So one of the reasons was the creation of tDataFrame, and tDataFrame wanted to create, to let users create data and write them out to disk in parallel, but to a single file, not to many files. So here, I will reach to the tDataFrame later, but let's first talk about writing columns in parallel. So this is pretty much equivalent to the parallel reading, but for writing things to disk. So if you have many different branches, you just parallelize, you launch a task, a TBB task for each branch, and things are done in parallel for you. And this is available since root 610. And compression can also be tackled in parallel, because as a part of the flushing of the baskets are compressed, so the compression happens in parallel also. So here we have a benchmark, also from Brian Bockamon. We have this data from CMS. We have both RICO and AOD data compared with no I/O. So if you look, for example, at reconstruction data, has a lot of branches, is very intensive in I/O. You have this curve for the event throughput, events per second. After some number of threads, which is, these are actually streams from CMSSW, which are proportional to number of threads, to 1.5. So it will plateau at around 30-something threads. But if you have RICO with IMT enabled, you can see that you can get a good, more or less, a bit more than 2x speed up. If you take a simpler data set, the AOD, it has less complexity in terms of number of branches. So then you have these 2 lines here. They approach this no I/O line, which is just writing out the, just cycling through the data but not writing it out. And there's not a huge difference between IMT enabled or not because there are not enough branches to parallelize on. So if you have 5 branches, this will not give you a lot of speed up. And this is implicit multi-threading, so the user doesn't have to write any special code for this. So then finally, I want to talk about how to write a file for multiple threads. This was the goal of TData Frame. We wanted to overcome this one file per thread paradigm, where you create a file, but you have to, one per thread, write to a different file. So then there is this handling of these mergeable objects behind the scenes. And here we'll talk about just T3. So it was created to support the snapshot action in parallel for TData Frame. And the initial idea actually existed in root, but for a network-based thing. It's called the T parallel merging file. And this was adapted to in GenV to use threads. And then we adopted that and worked on it and put it into root. So now it's also gathering some interest in CMS. We're discussing how to improve and optimize it and customize. One of the things is that there's no control. Well, I think I need to explain how it works first, but and then I'll mention this. So the new class is called the T-buffer merger, and it's basically just a factory of things that look like TMEM files, but when you write on them, they put the data on a queue. So this has been added in root 610. So here I have some schematics. So this is the T-buffer merger class. So you create your worker threads. They have some data buffer. It's something that looks like a T file that you get from the merger. And whenever you call write, it sends the data to some queue. And then there is a separate thread that picks this data and just writes them to disk in the background. And when everybody's done, there is a sentinel that is sent. And when the merger finds the sentinel, it closes the file. So here I have a sample code for how to use this thing. So the model, we wanted to create something that would be very familiar for users. So if you have here, for example, a function where you create some branch and you fill a tree and so on. So then you create a T file, you create your tree, then you fill your entries, you write, and then you're done. So here you can see that this is a very similar pattern. So you get a file from this merger class that you create with the name of the final file that you want. And then you create your workers with this part with a similar thing that you would do in a single-threaded mode. So then you create your tree, you fill the tree, and then you write. And at the end, when you create these workers, then you join them, and at the end, all of the data is just inside this one file. So you can use TBB tests or standard threads. This is not limited by so the programming model is up to the user how to parallelize. So here I have an example, a benchmark. So I wanted to emphasize the I/O on this, so I just created some file with random data in one branch. So just filled it with random numbers. It's just a synthetic benchmark. It's about 1 GB of data, and writing it out to SSD and directly to memory. So this is just my own laptop, just a quad-core machine. And you can see scaling is more or less, if you look at 4 cores and 1 core, it's pretty good. And here is, so the field markers are for compressed data, and the empty markers are for uncompressed. And you can see here that for an SSD, this is just the runtime, considering root, startup, and everything. So if you divide the file size by the runtime, you have some sort of rate that you can measure. And this reaches more or less 300 megabytes per second, which is almost saturating the speed of the SSD. And if I ran this also on a bigger server with an NVMe disk, comparing with a hard disk, and you can get, just from moving to a speedier media, just 4x speed up. And with not so many threads, I think it was about 12 or 14 threads, I could also saturate the NVMe disk writing this data. And this sort of benchmark is now being used to optimize parallelism in the I/O system. So we had something that looked like this. So I create many threads to create data. This is when they're busy. And there's some interaction here with the output thread that is writing the I/O to disk. So you see that you have some startup time for root here, loading shared libraries and so on. Then you write all this data, and then this output thread is still active for a little bit, writing the data. So if you pick faster storage, you decrease this time here. And if you improve, so this was there was some problems with interactions taking mutex locks. And using this, we managed to improve the situation. And we know how to get here, and then we're targeting these changes for root 612. However, there are still some thread safety issues within root that we have to resolve to be able to reach this more performant version of the code. So we hope that by 612, the experiments can find more performant I/O writing out to disk for the data. So before I finish, just an interlude. Sometimes you scale up even beyond the one machine, and then you have to end up with many files, because in each computer you create a file. You want to merge them. So HAD was parallelized, as mentioned before, and just like make, you can just give -jn. It will use multiprocessing and not multi-threading via tprocess executor. This is also released in root 610. So bottom line, root continues to make efforts to parallelize the I/O system, focus not only on the experiments data processing, but also on the last mile, the analysis for the users with the T-data frame and the writing data in parallel. You can create branches and just write them, extend your data set, or create new data sets using generators by starting from scratch with the T-data frame. So you can get some good speed up by reading and writing branches in parallel. And we added this new class to support writing out for T-data frame. And we have still more challenges ahead of us. We need to optimize parallel merging, as the figure I showed. We need to fix a few bugs for thread safety. And we want to also exploit better data parallelism via vector instructions, for example, by making use of vectorized compression decompression algorithms. And that's it. Any questions?
This might be that I didn't listen closely enough, but all those benchmarks were on SSDs, right?
Yes.
Does this extreme parallelization, even at the file level, as drawbacks on good old spinning disks?
Well, the drawback is the spinning disk itself, right? It's just slow. So you can saturate it with few threads. Doesn't matter if you have KNL. If you're writing to a slow disk, then you cannot scale. But then if you go to very fast NVMe disk, for example, you can get good speed up.
Sure. No, my point was more like compared to the one thread per file implementation, does this stay the same or does it get worse? Since you do random.
So you want to know the relative overhead of writing multiple files to using this merging?
Yeah.
So yes, I did a test with this, and up to 30 threads, this approach wins. So
even with spinning disks? Even
for spinning disks. So I ran on a big server, and it was faster to merge the data and write a single file than to. You have to keep. If you're writing to many files, every thread you get more system calls, and the system calls, they create more overhead. So.
Thanks.
So the multiple T data frames, how much buffering space is each one of those taking? And say, does it scale as per branch? And what I guess I'm worried about is if you keep full empty T baskets, your memory will explode as the number of branches for large data files.
Yeah, so in T-data frame, there is a mechanism to limit the amount of memory that you use. In the T-buffer merger, you really have to call write when you have enough data. And that's one of the things that we were discussing with CMS. Some sort of mechanism to not let the memory blow up. So as you reach some limit, you will block the threads. Because let's say you're on KML, and you can generate data much faster than you can write to disk. Then at some point, you're going to blow up your data, your memory. So then you need to really block the worker threads until you can flush everything to disk, and then you let them run and generate more data. Or if you're inside the framework, for example, in CMSSW, then you can let the writing thread put all the data on disk, and the framework can do some other kind of work that will not put even more pressure on the disk. All right, thank you.